Hey everyone, so we're going to continue with the question that we just worked on before, dealing with thermal radiation and that whole Planck distribution and photon stuff. So we're still using that same stuff and we're going to continue doing a few questions. So pause the video, work on this question yourself, and we'll go over it in a second. All right, so they want us to show that the sun can be treated as a black body that has this temperature. And they give us a bunch of other information, such as the distance between the Earth and the sun and the radius of the sun. So the way we're going to do this is we're going to use the energy flux that we got before. Now, this number is always constant. No matter what location you are, the energy flux is going to be the same. Things like the solar constant or the energy flux density will change depending on your location. This number wouldn't. So from here, these are some of the pieces of information that we have. So for example, one thing that we know is this, that the energy flux density, which we already said was the energy flux divided by the area, is also, if it's a black body, equal to this. So we're just going to see if that's true. So we know what all these terms are. So we plug the numbers in. We plug in the energy flux that we got from part A, the Boltzmann constant, and the radius of the sun. And then what we're going to do is get this temperature, or I shouldn't say this is temperature, this is T to the fourth. So when we quad root it, um, square root to the fourth power, what we end up getting is 5,818 Kelvin, which is approximately equal to 6,000. So by setting this generic definition for energy flux density equal to our definition of a black body radiation setup, we get that the sun actually could be considered a black body that is working at this temperature. So that's the whole thing. I was just going to say really quick is that this equation, this type of stuff is what we're going to be doing a lot. So this typically gets used when we're talking about, being at a surface of something. And then this would be through the location, some distance away from a star. But the whole thing is that this energy flux right here is what's going to be the linchpin between finding out information from on the surface to a location. So, for example, what we can do is we can use this information with the what we know about the information of the energy density at the Earth caused by the sun to figure out the temperature at the sun, and then we can kind of relate this back to figuring out what the temperature is at other locations around, or what the energy flux density is at other locations around the solar system. All right, so here's another question dealing with this type of stuff. So you could pause the video, work on the stuff, and we'll go over it in a second. All right, so here we're gonna pretty much try to calculate now the surface at the Earth. Now we're gonna assume that the Earth is a black body, and we're also gonna say that it radiates just as much energy as it receives from the sun. So this is going to be an important thing that we're going to relate. But one thing to note is that, as you'll see in a bit, that when we receive the energy, we're only receiving on part of the Earth, but we're going to assume that we're radiating all around the Earth. All right. So they give us this information. Again, a lot of this stuff is stuff that we got from before. All right. So from here, now this is a little bit confusing at first, so I just want to explain because I kind of skip a step. But this is the energy flux density caused by the Earth. The way this is going to be done is we're going to take the energy flux that the Earth is receiving and dividing it by the area, the surface area of the Earth. So that's what this is dealing with, or the surface area at the Earth's location. Um, so that's what this is all about. So when we plug in the equation for the surface area um, at the surface of the sun divided by the surface area at the location of the Earth, we end up getting this relationship. Uh, and then that can simplify to look something like this. So again, this term right here is just being used in place of the phi from before, the uh, energy flux, and then we're just dividing it by the this instead of just leaving it all as phi by itself. So what we have is that the energy received by the Earth is going to be equal to the energy radiated by the Earth. So the energy received is going to be equal to this. So it's receiving the energy flux density times the surface of the Earth that is observing the sun. So this is what I said before about the dimension or the part of the Earth that's absorbing the energy versus the part that's radiating the energy are actually different. Otherwise, we wouldn't even really be dealing with this. So um, if you kind of try to visualize it, when the sun hits the earth, it's pretty much only taking up a circle of the area. So it's absorbing a circle of the entire energy flux density at the location of the earth. But when it starts to radiate the energy, it's going to radiate along the surface of the earth. So that's what these two terms are. So this is the part of the energy that the Earth is basically taking a small little circle of radius re, while this is it radiating that same energy across the entire surface of its spherical shape. Yeah, so here this kind of says it again that the Earth intercepts the energy as a two-dimensional circuit, but then but radiates it in three dimensions. So from here, setting these two equal to each other, we can move some terms around and find that the temperature of these at the surface of the Earth is going to be equal to this times the temperature at the surface of the Sun. When we plug the numbers in, we end up getting about 280 Kelvin. So it does end up being a very, very small number compared to the temperature of the sun, that is. All right. Okay, here's the next question. Pause the video, work on the stuff, and we'll go over in a second. All right, so this again, we're taking the whole idea of the thermal radiation and taking it one step further and relating it to the fact that the sun is converting energy from hydrogen into helium. And they say that the reaction is going to stop when 10% of whatever the original hydrogen is turned into helium. And they give us the Einstein energy equation here that the difference in the mass is going to give us the energy available to the sun. So first off, we need to figure out what the original number of molecules of hydrogen was. So the number of hydrogen molecules, well, the entire mass of the sun is turned into was originally hydrogen. Divide the two numbers, and we get this. So this is the number of hydrogen molecules. Now we know that 10% of this hydrogen is going to be turned into helium. So we take 10% of that and we get this. This is the number of helium that's going to be produced. Now what we're going to do is the change in the mass would be equal to the number of the amount of hydrogen that was combined minus the amount of helium that we end up getting, the mass values. And we get the difference in mass is equal to this, 0.0286 AMU, which is also equal to this number of kilograms. So from here, we can find the energy being equal to this. So from here, we end up getting that the energy is going to be 5.11 times 10 to the 44th joules. All right, here's the next part. You can pause the video, work on this up, and we'll go over in a second. All right, so we know how much energy is available going from hydrogen into helium. And we know that once it gets to that amount of energy, it's going to stop. We know what the energy output is of the sun. So just use that definition. Time is just the energy available divided by the energy output of the sun. And we get that it's going to be equal to 4 times 10 to the 10 years. So that is the life expectancy of the sun. All right. So I'm going to mention something real quick called the Debye theory. This is actually very similar to what we literally just talked about with the photons, but we are going to have to change some things around. So as you remember, the whole idea with the Planck radiation was that light comes in photons, and they create this equilibrium state within these cavities, and that's what's going to cause the thermal equilibrium. So we could actually do something very similar, talking about mechanical waves going through solids. And we're going to call these, instead of calling them photons, will be phonons. So these phonons are the elastic waves that are traveling through solids, and they're basically going to be doing the same thing. So the average phonon uh, of the elastic waves is actually going to be very similar and get us the same relationship as the average number of photons being equal to this. So the Planck distribution works the same way for the light form of photons and the elastic wave mechanical of phonons. Now, one thing just to make our lives a little bit easy that we're going to assume is that the waves, these elastic waves, are going to be traveling with constant speeds. So regardless of frequency, direction, propagation. So of course these things will change, but we're going to just assume that it's all the same. Now there is going to be some differences between the phonons and the photons, which is why not everything is going to be the same. So for example, one thing is that with phonons, there is a finite possible number that we can have, based off of things like the physical aspect of it. With photons, we could just keep sending in more and more. We can have an infinite number, but here we actually will have a finite number phonons possible. So what we're going to say is that since a solid is consisting of n particles and each particle has 3 degrees of freedom, then we can have at most the number of modes being 3n. Because, with each particle with 3 different degrees of freedom. That's pretty much it. Now there is another thing that we have to note is that with elastic waves, so we said before that the photons only had 2 forms of polarization. I don't think I clarified exactly what I meant by that, but for example, it can pretty much it travels in, let's say, in the z direction, and it could be in either the x or the y direction essentially. So it only really has the 2 transverse forms, being transverse in the x or transverse in the y. It can't really be transverse in the z because that's really the direction it's moving in. But here, elastic waves actually have 3 polarizations. So the elastic waves can be the 2 transverse, just like with the light waves, but elastic waves can also come in the form of longitudinal. So in this case, it actually can go in that z direction as well as a longitudinal wave. So the if you remember that density equation that we had for the photons was equal to this, and this was for two forms of polarization, two modes. But for phonons, which are three, is going to be equal to this. So some slight differences. It's now three halves instead of nothing, or instead of one. And then we're changing the c into vs, which would be the speed through the solid. All right. So there is a finite number of frequencies that are allowed, and what we're going to say is that there's going to be a cutoff at this dBi frequency. So this is going to be the highest frequency that's going to allow vibrations. And I think that's the important thing, that if you go higher than this frequency, it's not going to end up, it's going to be too high to actually vibrate the molecules. So that's what it's trying to get at, is that there's a limit to how much frequency we can send in to actually vibrate the molecules. And that's what that dBi frequency is. All right. So the way we're going to figure this out is by integrating the density of the modes, and then we're going to set it equal to the total number of modes that are available. So we know that the total number is equal to 3n. So we integrate the mode density, going from 0 to our cutoff frequency. So we end up getting this. This simplifies, or this integrates to this term, just omega cubed, getting rid of that 3 over there. And then we just solve for omega, the dBi frequency. So either one of these works out. That we end up getting this. We could actually replace the n over v with the concentration, but you might not want to mix up your variables. All right. So if we look at the equation that we had for the phonon density, so that we kind of get rid of this the velocity aspect, we can plug in the equation that we had for the velocity as a function of the dBi frequency, plug it back into here, and we end up getting this really nice relationship between the number of molecules, the current frequency, and the cutoff frequency. We can use this just like before, by integrating the average energy to find the total energy. Again, going from 0 to the cutoff frequency, plugging in the pretty much the again doing a lot of the same steps that we've done before. We can get rid of the dBi frequency, and we're just left with this stuff. Again, you should know how to integrate this, because we can kind of do a x substitution for this. So here we're going to define x as being equal to this term, and then we're also going to define xd to be equal to this. You'll see why in a second. And then we're going to have this term because be equal to this theta term. So xd is going to be equal to theta over t. This is going to be representing what we call the dBi temperature. So again, what we end up having is all this stuff. Going back to our energy equation that we had, make all our proper substitutions, pulling out everything that we have once again this thing that we've integrated before. Now here, because there is somewhat of a limit, we're going to have to consider two different cases. So there's the low temperature case, where the actual temperature is going to be much smaller than the dBi temperature. So that means what we can say is that xd is extremely large and can be roughly equal to infinity. So this integration is going to just be that pi to the fourth over 15 that we've seen before. So we end up getting this is the energy for low temperatures, simplified to this. Um, and then we could find that heat capacity by taking that equation that we have for the temperature and integrating it, or taking the derivative with respect to tau. So we'd have to change the t in there into tau, but we end up getting this for the heat capacity, again at low temperatures, which can also be rewritten like this, again at low temperatures. This relationship that the heat capacity is proportional to the temperature cubed is sometimes called as the Debye T cubed law. All right, so pause video, work on this stuff, and we'll go over it in a second. All right, so what we're going to do here is we're going to um, determine the temperature of the photon contribution, and what it would have to be in order to be equal to the phonon contribution of energy at 1 Kelvin. All right, so they give us this information. We know that the Debye temperature is 100 Kelvin. We know that the concentration is equal to this, and we know that the phonon temperature is 1 Kelvin. So the heat capacity, if you recall, is just the derivative of the energy with respect to temperature. So we take the equation that we have for the photon contribution, and we're going to take the derivative with respect to the tau. When we get this, then we set that equal to our phonon contribution that we have. And then, so setting this equation equal to this and solving for the photon temperature. I know it's a little confusing with some of the stuff. Plug in the numbers in that we're given. We end up getting that the photon contribution is 2.22 times 10 to the 5th Kelvin. So that would be the temperature needed so that the photon contribution is equal to the phonon contribution at 1 Kelvin. So there's a few more questions that we're going to be doing, so this video might be a little bit longer, so just bear with me. Here's the next question. Pause the video, work on yourself, and we'll go over in a second. All right, so we're using, they give us this hint for the whole heat capacity. So they give us all this information. Again, they give us the temperature, they give us the concentration. So we know that the specific heat caused by the hydrogen is just going to be found using this equation. This is from the photon radiation that we had before. Take the derivative of the internal energy, essentially the specific heat for typical matter. That's what they called it, and divide by that photon specific heat that we had before to get this. Plug in the numbers in, and we get that it is roughly about 10 to the negative 9. All right. Here's the next question. Pause the video, work on the cell phone. We'll go over in a second. All right. So here they give us this information. So they want to find the Debye temperature. So if you remember, the Debye temperature is found by doing this. using the Debye frequency in this equation. And then the Debye frequency has an equation related to the speed of the wave. So in here, we're actually talking specifically about sound waves. So we end up getting this, plugging the numbers in, and we get that the Debye temperature is 19.8 Kelvin. All right, here's the next question. Pause the video, work on itself, and we'll go in a second. All right, so what we're going to do is use the specific heat for using the Debye theory like this. So this is what we had before, and I don't really think there's much that we can do. We're going to leave the t cubed out just like they had here so that we can compare the constant numbers. And then I think that's pretty much it. Oh, we have to take the number of n and replace it with this, Avogadro's number divided by the molar mass, because you can actually see through unit analysis that that's what you end up getting. So that's what's going on here. Just replacing the n with the calculating the number of molecules through Avogadro's number, the molar mass, plugging the numbers in, and you end up getting this. And then since they said that there's no transverse waves, we're going to take this and divide it by 3. And that's where we get the 0.0204. So again, one good thing that you can do is if you know since we know what the answer is, what you're going to want to do is try to compare this and say, okay, well, how could I go from here to here? Clearly I have the t cubed part. The only thing that's missing is this. And then you notice, oh, this looks like it's just a factor of 3 compared to this. And then that will kind of hint back to what they said before here, that it's only a longitudinal wave and that there's no transverse waves, which remember is 2 of the 3 waves. So we're only talking about 1 of the 3. So that kind of hints as to what you're going to end up doing. So here's a summary of all the stuff that we've talked about. The main stuff are the equations for photon distribution and phonon distribution. All this stuff with energy flux density. Typically, this stuff gets used a lot with planetary things, black body radiation type stuff, which we normally can only see on the cosmic scale. So a lot of times, if you start seeing stuff that's dealing in the galaxy or in a solar system, this is usually the equation that you're going to be working with. Then we have these equations, and then this is the homework for chapter 4, 3 questions where you get to practice a lot of this stuff. Once again, if you have any questions, please let me know. Otherwise, I'll see you in the next video. Bye.